Okay, so one of the things that you had before was the normal distribution. We talked about this last time in the normal distribution. In other words, what we did was this. We talked about, we had a sample, a population, and we had a sample, it was normal. Now, what we did was, we had to find probabilities of this population. So let's say that the population was normal, and we said, well, what's the probability that a value is going to be greater than 30? Now that's given that your mean was, let's say, 25, and your standard deviation was 5. Okay, so we want to find out what is the probability it's going to be greater than 30. So our first step was to convert this into a z-score. So we had 30 minus 25 divided by 5. That was your standard normal score, the z-score. So we have 30 minus 25 is 5, divided by 5 is equal to 1. Okay? So we have that. Now that means that this translates down to the probability that z is greater than or equal to 1. So now we want to look at that, and we can look at it on the computer or the tables or the calculator. I'm just going to do the calculator. And we went second in vars. Okay, second in vars. We went out to normal CDF. We went over to 1 all the way out to infinity. And the way we translate infinity is 1 e to the 99. And press enter. And we get that our probability is 0.1587. So what is that 0.1587? Well, it's greater than 1. Any area out here that's greater than 1. Okay, so that's going to be your probability right there. So this 0.1587 is going to be this right here. Now, the other thing we did was the inverse norm. And on the inverse norm, we said, okay, well, at this time, let's say it was normal distribution with a mean of 30 and a standard deviation of 5. And we want to find out the top 15%. Okay, so we wanted to find out the top 15%. So let's say that this is the top 15% right there. So what we want to do is get the rest. And the rest is going to be 0.85, because 1 minus 0.15 should give you 0.85. Okay, so that's 5. That's 9. Okay, so that's 85. So it's going to be 0.85 right there. Okay, so basically we have the 85%. So now what we have to do is find the z-score that goes with it. So we go second in vars, go to inverse norm, okay, press enter, and put in 0.85. Press enter, you get 1.04. So the z-score right here is 1.04. Now you have to convert it into a raw score with a mean of 30 and a standard deviation of 5. So our raw score is going to be the mean plus the z-score times the standard deviation. So what we have is 30 plus 1.04 times the standard deviation of 5. So we go ahead and calculate that. We have 30 plus 1.04 times, and that's going to be 5. And you get 35.2. So the answer is 35.2. And that's what we did last time. Okay? Now, what we're going to do today is we're going to look at another thing. Now, why do we do this? Well, in Chapter 7, 8, and 9, we're going to be talking about finding. Okay, so this is what we're doing in Chapter 7, 8, and 9. In Chapter 7, we have a population. We want to know what a population mean is. We have no clue. But so what can we do? Well, we can take a sample. Okay, we can take a sample of that. And that's going to become our point estimator. We're going to say, okay, so our population mean has to be somewhere close by to this sample mean. So what we're doing is we're tying in those two values. The way we do it is through the central limit theorem. Okay? So that's where we're going now. Now, before we do this, let's go ahead and I'm not sure whether to do this first or to do that. So I'm going to do the activity first. So before we do this, let's go ahead and do the activity. Okay? There we go. Okay, so what this activity is to show you a little bit of what the central limit theorem is. Now you can group up with each other. Go ahead and take a partner, and you can go ahead and help each other. And then if you don't mind going with hand number here. Okay, so what we're going to be doing here is we're going to be, let's look at the first part of it. Okay, and I'll do this with you, sort of. Now, what you need to do here is this. You got these people, and they have the total number of sick days taken by each employee last year is recorded below. Okay, so what I have to do is I record what each one had. So Alice missed 7 days. Okay, Alice missed 7 days. Now Ben missed 8 days. Okay, Chelsea missed 6 days. Daniel missed 8 days. And Ethan missed 7 days. Okay, so that's what we have. So now what we're going to do is we're going to see, okay, so what are your x values? Well, you have 6, 7, and 8. So you have 6, 7, and 8, like that. So now we want to find the probability. So you have 1, 2, 3, 4, 5 people. So how many, okay, so the probability of him missing a day is, well, let's see. There is what? 1, 2, 3, 4, 5. 1 divided by what? 5. That's your probability. How about 7? What's the probability of missing 7 days? There's 2 of them out of 5, so that becomes 2 divided by 5. Okay? So those are your answers like that. So go ahead and finish the other ones. We're doing it that way. So we had 1 divided by 5. We had 2 divided by 5. Okay, and we have how many 8s? 2 divided by 5. Okay, so we have that. What is your population size? Well, how many people do you have there?
5.
Okay, so it's going to be 5. What is your population mean? Well, what you're going to do is add all these numbers together and divide by how many you had. So add 7, 8, 6, 8, and 7, and divide it by 5. Then that gives you your population mean. And your standard deviation. Now there's another way of doing that, and what was that? Remember? We could go over here. We could go to Stat and Edit. Okay, we could press clear on this. Clear on that. Clear on this. And then what should we do? We could put 7, 8, 6, 8, and 7, and then go to Stat and Calc, and one variable Stats, and L1. Okay, so we get that our mean is going to be what? 7.2, and so our population mean is going to be 7.2, and what is our population standard deviation going to be? 0.7483, that's right. So that's going to be your population standard deviation. So that's the first one. So now that gives you your population numbers, okay? So we have the mean is going to be 7.2 on that one, and the standard deviation is going to be 0.7483. Okay? So any questions on that? Okay, so now I'm going to do is a sample each one of those. So notice how you have A, B, C. So what that means is we're going to take A. So A was Alice, and she was 7 days missing. Okay, then B was Ben. He was 8 days missing. And then we have Chelsea. Chelsea was 6 days missing. So that's going to... Well, we're going to add them together. We have 7 plus 8 plus 6. Okay, and then we're going to divide it by 3. That gives you your average. So the average, the sample mean for the 3 is 7. Okay, so what about the next one? The next one's Alice, Ben, and Daniel.
7 plus 8 plus 8.
So Alice is 7, Ben is 8, and Daniel was 8. So add them together and divide by 3 and see what you get. So you can, right, so you're going to do that for all of those, okay, and find their sample means. So go ahead and do that. Yes.
Round?
Anybody get the next one?
7.67. Oh, wait.
7.33.
7.33.
And then 7.
Okay, 7. What about this one?
6.67.
Okay. What about this one?
7.32.
Okay, what about the next one?
7.52.
Okay, what about the next one?
7. 7.67. And 7.
And then 7. Okay. So we get all these numbers. Now what we have to do here is find out, okay, well, let's see what's in common. We have a 6.666, right? One of those means. Our next mean is what? 7.0. The next one is what? 7.333. And what's the last one? 7.667, I guess you would call it.
Should
Yes.
we change it if we rounded those numbers? Should we put it in that instead of rounding?
No, just what you have. It'll be a little bit of a difference because of the rounding, but it won't be that much. Okay, so now, how many times does 6.66 happen?
1.
1 out of 10 then. That's your probability. How many times did 7 happen?
4 out of 10.
I'm sorry?
4 out of 10.
Okay, so 4 out of 10. So that's your probability on that one. What about 7.33333 repeating?
3 out of 10.
Okay, so 3/10. Okay, and then what about 7.6667?
2 out of 10.
2 out of 10. Okay, so that's what we have. That's your probability distribution. What you're going to do here is you're just going to draw it out, okay? So we have 6.66, so it's going to be somewhere in here, okay? Now, so that one, it's going to be 1/10, so that's going to be 1.1. So you're going to have a bar going like this, okay? Now, what about the next one? What about 7? What about 7? We have 4/10, so that's going to be up to what?
4.
0.4. Okay, so we're going to have something like that. And this is kind of guesstimating, okay? What about 7.333? That's 3/10, so it's going to be around here, right? And yeah. And then we have 7.666, and that's going to be what? 2/10 like that. So you're going to have a distribution like that, correct? So that's what we're doing there. Basically, what I want you to understand is that from this values, the sample mean values, we found a probability distribution of these sample means, okay? And we made a representation of it through graphs, through a graph. What is your sample size each time?
10.
Okay. Sample size each time is 3, right? Okay, to find the mean of the distribution and the standard deviation of the distribution, which we call the standard error, we want to put these numbers into the calculator. So we have stat and edit. I'm going to clear this off. I'm going to put in 6.6667. We have 7. We have 7.33. That's going to be 3. We have 6.6667. Okay, so we have those numbers, right? And then on the other one, I'm going to put my probabilities. 1 divided by 10. 4 divided by 10. What's that? 3 divided by 10. And 2 divided by 10, correct? And we're going to have stat, calc, one variable stats, L1, comma, L2. What is the mean of this distribution? 7.2, isn't it? So this is the mean of the distribution of these sample means. Do you see that? That's the mean of the distribution of all those sample means. I just want you to see if you can understand that, because basically what we're going to be doing is, well, I'll take it in a little bit, but we took samples. We took samples out of this population, okay? And we found that if we took these samples, we found a few commonalities. We found just 4 variables, and we found probabilities for each one of those variables, right? For all those means. These are the sample means. So we found our probability distribution for all the sample means. And now we can find the mean of the means of the sampling means. Okay, we found the mean of the sample means. And that was what? That was 7.2, right? What about this one? This is called the standard error. This is a symbol you're going to be tested on. Sigma sub x bar. That's called the standard error. And the definition of the standard error is the standard of deviation of the distribution of sampling means, of sample means. So in other words, you have your population right here. Let me go ahead and look at this again. Let's look at this. You have a population right there, okay? And you want to find the population mean. You don't know what it is, but you want to find it. So what you can do is take a sample mean. Well, is that sample mean equal to that one? Maybe, but maybe not, because you don't have all of them. So let's take another sample. Well, we have another sample mean. In another sample, 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 in another sample. So what we're doing is we're taking all these samples and we're finding the probability distribution of all those sample means. And what this is, that the mean of all those sampling means, okay, is going to be the same as that one right there. Notice, that's 7.2, right? What was the mean for the one over here? I didn't have it, but what did you get for that mean, for the first one?
7.2.
7.2. They were the same, right? So that's the first part of a theorem that you're going to be seeing. Okay, the other thing we have is this. So now we have this right here. Okay, so now tell me, what is your standard of deviation? Let me see, where did I put it? I put it over here, right? So where is that standard of deviation? What is that going to be? Okay, so it's 0.3055, right? So now this is a little bit more simple because we're counting right here, right? So it's finite. So let's look at the back and look what you see on the back. Okay? Now, so let's look at this right here. We have, well, you tell me, what is called a population mean? Which one of those symbols is the population mean? The mu, that's correct. Okay, so which one is called the mean of the sampling mean? Based on this right here. Based on what I just told you about this.
The mu x bar.
Mu sub x bar, that's correct. Okay, what is called a population standard of deviation? The sigma, right? Or the O with a little hat on it. What is called the standard error?
The sigma with the
The sigma sub x bar, that is correct. So what is the balance point for all individual data values? That's your mean. Okay? So the balance point is always the mean. So what do you think the balance point for the sampling means is?
mu x bar.
The mu sub x bar, that's correct. The mean of a sample means. Measures how spread out the individual data values are. So individual data values, which one do you think it's going to be? The spreading of it. The standard deviation, that's correct. Which one measures how spread out the sample means are?
Sigma with the x.
The standard error, that's right. The sigma sub x bar. Okay, that's called the standard error. Okay? And it's called the standard error of the means. Which one is it? I'm saying it.
Sigma x bar.
Sigma sub x bar. That's the standard error. Okay, so now let me ask you this. Is the mean of the sampling mean equal to the population mean? Well, you told me that already.
Yes.
Okay, good. So yes, that is correct. Is the standard error of the mean equal to the population standard deviation?
No.
No, it's not. Okay, so we're going to calculate it. Now, this is a little bit different than what you're going to do, because what we're going to have, and I'm going to show you another one that's going to be closer to what you're doing, but this one is for finite numbers, okay? So we have to calculate a little bit different. Okay, so but before we do that, let's look at this. Which of the following is true? This one, or this one? The mean of the sample means is less than the mean, the population mean. The mean of the sample means is equal to the population mean. The mean of the sample mean is greater than the population mean.
Equal.
They're equal, that's correct. Okay, so now look at this one. Which of the following is true?
Less than.
Okay, so it's going to be less than, right? Okay, good. Now, is the population in this example finite or infinite? It's finite. So put finite.
What does finite mean?
It means that the numbers are counts. You're counting 7 days, 8 days, 6 days. What was the value of sigma sub x bar?
0.3055.
0.3055. Now it doesn't say here, but what is? Let's look at what is the one for your population.
0.7483.
Okay. So now calculate it in here. Do you see how you got? What is your big N? Your big N is your 5. You got 5 people: Alice, Ben, Chelsea, Daniel, and Ethan. I'll do it with you, okay? So now we have this. We have 0.7483 divided by the square root of 3, because we have 3 people each time. Each sample had 3. Remember? Right here, we had A, B, C, A, B, D, A, B, E. So we had 3 each time. So we have 3 on there. Times the square root of, now N is your population size, which is 5, minus 3, divided by 5 minus 1. Okay, so now what does that give you? Let's calculate it. So we have 0.7483 divided by the square root of 3. Okay, so it's going to give me 0.4320. And then this one, 5 minus 3 is 2. 5 minus 1 is 4, right?
Yes.
So 2 divided by 4, that gives us a half. We have to square root that half. And we get something like 0.7071, right? Now I'm rounding to 4 decimal places, so it's going to be a little bit off. So I'm going to multiply those two numbers. So I'm going to multiply that times 0.4320. So that's going to give me what? 0.30 what? 55. Okay, so it's 0.3055.
The same as the.
So that's the same as the standard error you calculated with that probability distribution, correct? Okay, so is sigma sub x bar equal to this right here? Yes, okay. And that's the end of this activity. What we're trying to do in this activity is to let you understand that what you're doing is, on our next phase, we have a distribution of all the sample means, okay? So we have sample mean after sample mean after sample mean after sample mean, and with that distribution, we found our standard error and our standard error, okay? And we found out that the mean of that sample means is equal to the mean of the population mean. Okay? Now I'm going to do another one right here. Let's look at this one right here. So go ahead and complete that. Go ahead and make sure you have everything on there, and I'm going to give you a grade for it. Okay? So turn it in. But now let's look at this one right here. What does that look like to you? Whoops. Okay, so what does that look like to you? What does that figure look like to you? Anything we've been doing last day? What's today? Monday? Last week?
Standard normal distribution.
That's your normal distribution. That's correct. Now, this normal distribution it's a population, and it's a population that has normally distributed. Okay, ding, 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 normally distributed. Okay, so that population is normally distributed. Okay, so and what this does, this is a simulation. And what we're going to do is we're going to take samples. We're going to take samples and we're going to find the sample mean and the sample standard deviation, okay, of it. And then we're going to take thousands and thousands of samples, and then we're going to find the mean of all those samples and the standard deviation of all those samples, okay? Now, this is continuous. So let's look at the first one. I'm just going to take 5 this time. And my sample size are going to be 3. I'm going to put 3 in them, okay? Because we did last time. We did 3. So I'm going to take a sample. I'm going to take 5. Well, I'm going to take 1 first. There's my first sample. I have 3 things in my sample. My sample mean was 27.902. My standard deviation was 3.2064. Okay? You see that? So my first one, I had 1 sample, and I just had that. Now, let's say that I'm going to take 5. So I'm going to take 5 more samples. Now I have 6 samples, right? Because I took that one and 5 more. Okay, so now I took 6 samples. My last sample, the mean was 26.57 with a standard deviation of 3.16. All 6 samples gave me a mean of 24.849 and a standard deviation of 2.2934. Now, do you see that there? Okay, so now I'm going to take 5 more. So now I have 11 samples. I took 11 samples. This is the way it looks like. This is its distribution of the sample means. And okay, so the mean of all the 11 sample means is 23.93 with a standard deviation of 2.62. Our standard error is 2.62 in this case. Where our population mean was 5 and our mean was 25. I mean, our standard deviation was 5 and the mean was 25. Does everybody understand what we're doing here? Now, instead of taking 5 at a time, I'm going to take 1,000 at a time. So now that means I'm going to take 1,011 samples. Okay? So here we go. Now that's really quick. So we take 1,000 samples. So now we have 1,011 samples. Do you see what I'm saying? I said, took a sample, 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 just sampling, 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 tons of samples. There's something very similar to this, which is what we call non-parametric statistics. It's called bootstrapping. If you ever go into what they call data analysis, you know, they have a lot of that for Google. Like Google and Facebook, they hire a lot of data analysis because what they do is they look at the data and they kind of fit the ads or whatever to what you like. Okay, so they look at the data. So that's what they're doing. Their data analysis, and this is one of the things they do. They look at distributions of samples. Okay, so basically, look at that distribution of that sample means. What does it look like? Let's take some more. Let's say we're going to take 1,000 more samples. Take more, take 1,000 more, take 1,000 more. Let me go ahead and take a lot more. So look what's happening as we take more and more samples. So now we've taken what? 46,011 samples. Each one is a 3. What does this distribution of the sample means look like?
Just like your population.
Just like the population one, right? So that's the first thing. And if you look at your Nearpod, okay, so I'm going to go to Nearpod here. And you look at this right here, that's what that theorem is talking about. Let x be a random variable with normal distribution with a mean of mu and a standard deviation of sigma. Let x bar be the sample mean corresponding to a random sample of size n taken from the distribution. That's what we did right here, okay? That's what that's talking about. Then it says, let x bar be let the x bar distribution, that means the distribution of the sample means, in other words, this one right here, be a normal distribution, okay? The mean of the x bar, so that's talking about this one right here, the mean of this one right here, the mean of this distribution of sample means, okay, is the same as your population mean. That's what that's saying. Same thing we discover right here. The mean right here is going to be the same as this one. See, it's very close to it, 24.99, 25. So they're kind of close to each other. If you did a lot more, let's go ahead and take 1,000 more so you'll see. See, it's moving to it. It's what we call limits. They used to have one that had 10,000, but now that they changed it. So let's look at that. That's 24.9889, which is very close to 25, right? Well, that's what that's saying. That's what this is saying right here. That the mean of the x-bar distributions, the mean here of this one right here, is going to be close to that mean of that population standard of that population mean. Okay, that's what that's saying right here. The standard of deviation of the x-bar distribution, sigma sub x-bar, the sigma divided by the square root of n, okay? If you take this one, go ahead and take that. Take 2.88. So take this. Take that. 2.8879 and divide it by the square root of 3, because we only had 3 in each sample, right? So we had that. And what does that give you? Oh, I'm sorry, that's not what we have. Take this one. Take this population standard of deviation right there. Take the 5. So 5, and take it divided by the square root of 3. I'm sorry. That's what we have to do. And what do you get?
2.886.
Right, which is very close to this one right here, right? So that's what we're talking about. So now the other part here, they're saying this, is that right there. The standard deviation of the distribution of sample means is equal to your population standard deviation divided by the square root of the sample size of each one of those samples. Okay, each one is the same size, okay? The standard deviation of the original distribution divided by the square root of the sample size. This is what we call the standard error. The sigma divided by the square root of n is called the standard error. That's important to know, because that's how you're going to be calculating standard scores now. Okay, so now we can use this theorem to draw conclusions about means of samples taken from normal distributions. If the original distribution is normal, then sampling distributions will be normal. In other words, this right here. Look what we had here. We started with a normal population. We had sample after sample. Of course, we got a normal distribution back, right? So that's what that's saying. That's what that theorem is saying right there. So any questions on that theorem? Okay, so now this is important. This symbol is important. That's called the mean of the sampling distribution. Okay, this is the mean of the sampling distribution. And this one, okay, so that mean of the sampling distribution is equal to the population mean. Now, this one, this is called the standard error. And the standard error is equal to the standard deviation, the population standard deviation, divided by the square root of your sample size. You need to know that part.
Can we go back and maybe take more notes at home?
I'm sorry?
Like, can we write all this down at home after class?
Yes, I'll put it on Nearpod.
Okay.
I'll put a code for it. Okay, so but you see what you have there? Now, so any questions on that part? Now, let's look at this. To calculate z-scores, what you're going to do is you're going to have, okay, so here's how the problem's going to happen. What you're going to have is this. Instead of saying, what's the probability of the individual score, it's going to say, what's the probability of the sample mean? Okay? That's the difference. That's where you know you're going to be able to use this right here. And what happens is that now your normal standard score is going to replace. Instead of subtracting from the population mean, you're going to be subtracting from the mean of the sampling distribution. Guess what? It's the same one. It's the same number. Okay? Divided by your standard error. Now this is what's going to change. Because instead of having just a standard deviation, you're going to take the standard deviation and and divided by the square root of the sample size. Okay, so that's what changes. Any questions on that? So let me give you an example. Let's look at this one right here. Now, let's look at this one. Assume the population of weights of men is normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Find the probability that if an individual man is randomly selected, his weight is greater than 175. So you've probably done this already at some point somehow. So let's look at the first one. I'm just going to do it here. So what you're going to do here is, what are your steps that we did before? This is like we did before.
E is greater than 175. X is greater than 175.
Okay. Before we do that, we're just going to write down our numbers. Our population mean is 172. Our standard deviation is 29. And we want to find the probability that a weight is greater than 175. Okay, so we have that. So this is what we want to find. So how do we find this? How do you find the standard score for that?
175 minus 172 over 29.
Right, so we have that x value. So it's 175 minus 172 divided by 29. Okay, so that gives us what?
1.734.
So that's going to be 179 minus 172 divided by, what did I say, 29? Didn't I get that?
175 instead of 170.
Yeah, I'm sorry. Here, let me see here. 170. No, wait a minute.
No, so what do we say?
No, it says this weight is greater than 175.
Oh, okay.
Yeah.
So it's 175 minus, the mean is 172, divided by the standard deviation, which was 29. Okay, so my z-score is going to be 0.10. That's my z-score, right? So that's what we're going to have. So now, what I have to do is do what?
Put it in distribution.
Right. So what I'm going to do is I'm going to do it in a calculator. So that's going to be greater than, so we're going to go on the right side. So it's going to be second in VARS, normal CDF. We're going to go so for 0.10 all the way out to infinity. So that's 1 e to the 99. Sorry, I didn't do the 1. 1 e to the 99 and press enter. And we get what? 0.4602. And that's your answer. The probability is going to be greater than 175 is going to be 46%. Pretty much so. Now that's what you did before. Now what we want to do is find the probability of a sample mean. So now we want to find the probability that 20 randomly selected men will have a mean weight that is greater than 175 pounds. Okay, so now look at the difference. Look at the difference between this one. Find the probability that an individual man, find the probability of a sample mean. Do you see that? That's key. That's when you look at the final exam or the next test, that's what you have to figure out. Okay, are they talking about an individual person? Or are they talking about a sample mean? Because if they're talking about an individual person, you're just going to divide by the standard deviation. There's no change. But if you're talking about the sample mean, then the only thing you have to do is divide by the standard error instead of the standard of deviation. And remember, your standard error is your standard deviation divided by the square root of your sample size. So in this case, what we're going to do is we're going to go ahead and say, okay, now we want to find the standard error. So the standard error is 29 divided by the square root of, what was my sample size there? 20. So the square root of 20. So what is that number going to be? We have 29 divided by the square root of 20.
6.48.
Okay, so now that's going to be 6.4846. So now what we're going to have, let me make sure it's the same numbers. Yes, 175. Now we're going to have this. We're going to have the probability that x bar is greater than 175. So now our formula changes to x bar minus the mean divided by my standard error, where my standard error was this one right here. See, that's my standard error. So now we have my x bar was 175 minus my population mean, which was 172, divided by the standard error, which was 6.4846. Okay, so now we have is that 175 minus 172 divided by 6.4846. And we get what? 0.46, right? So we get that. We get about 0.46. And now what we're going to do is we're going to say, okay, now we have to find second inverse normal CDF. We're going from 0.46 out to infinity. Okay, so we're going to have 0.46 all the way out to infinity. Second e to the 99. Enter. And you get what? 0.3228. And that's your answer. Any question of this?
Is that it?
Okay, so that's going to be your answer for that one, yes. Okay, so now, the individual one is 46%. The mean is going to be 32.28%. Okay? So you're going to have some questions like this on the test and on the final exam. So make sure you know them. Okay. Let's try this one. The time it takes to drive city A and B is normally distributed with a mean of 14 minutes and a standard deviation of 2.2 minutes. Find the probability that a trip between the cities takes more than 15 minutes. And find the probability that the mean time of 9 trips between the cities is more than 15 minutes. So I'm going to give you some time to do that one. And what you're doing now, I'll collect those activities. Give you a break for it. your names on them.
Wait, hold on. Okay, so I keep that right. Just keep that right. No, it's okay. So that's gonna be the new one. Or, what is that? So that's the main. Exit the line, right?
Okay, so let me go ahead and do this one because we're kind of running out of time. So now, our first step is, this is what you do. You're going to approach this, you have this problem right here, okay? So you're going to go ahead and, first of all, write the mean and the standard of deviation. That's important, okay? So when you approach this, write down the mean and the standard of deviation. Okay, so in our first, this is what we have. We have, okay, the mean is 14, and the standard deviation is 2.2. Okay? Now, our next step is going to say, okay, so what is the probability? Find the probability that a trip, one trip between the city takes more than 15 minutes. So find the probability that x is greater than 15. Okay? First step. Now we're going to go ahead and convert this into a z-score. So we have x minus the mean divided by the standard of deviation. Okay? So that's going to be 15 minus 14 divided by 2.2. Which gives us what? So we're going to have 15 minus 14 divided by 2.2, that's going to give us 0.45. Now, what we're going to do is find that probability. Okay, so we're going to go ahead and find that probability right there. So that's going to be the probability that z is greater than 0.45. Notice how it's changed. Now, it used to be 15, now it's 0.45. It used to be x, now it's z. So we're going to go to our calculator. So we go to our calculator and we go over here and we say second inverse normal CDF 0.45 comma 1 e to the 99 and press enter. And we get what for our answer? Right, 0.3264. That's correct. And that is our answer for that one. Now let's look at the next one. The next one says find the probability. Okay, so look at this one because this is going to be the important part. Find the probability that the mean time of 9 trips between the cities is more than 15. So now what you have is this. Now what you have is find the probability that the mean time of those is going to be more than 15. Okay. Now we have that the mean is still 14 and the standard deviation is 2.2. But we have 9 now because we had 9 trips. So now our next step is going to be to convert that z-score. In order to do that, we have to find our standard error. We find our standard error by taking the standard deviation and dividing it by the square root of n, our sample size. So that's going to be 2.2 divided by, can we agree that square root of 9 is 3? So it's going to be divided by 3, right? So we're going to have 2.2 divided by 3, and that's going to give us 0.73 repeating. Okay? Now we calculate the z-score, the standard score, which is x bar minus the mean divided by the standard error. It's the same numbers. You have 15 minus 14 divided by 0.73 repeating. So now that's going to be what? 15 minus 14 divided by 0.73. That gives us what?
1.3637.
That's right. So we're going to go ahead and round it off to 1.36. So what happens here is that this changes to the probability that z is greater than 1.36. And now we just find that probability. We go to our calculator. We go over here. We go second and vars. Go to normal CDF. Go 1.36 comma to 1 E99 and press enter. And you get what as your answer? 0.0869. That's right. Now I might have, let's see here, what is 15 minus 14? There's a rounding difference error, so divided by 0.7. They rounded to 1.37, but it rounds to 1.36. Okay? So it's 1.36 there. So that gives us this probability. So are there any questions on that? Now, what if the central limit, let's look at this again. What if you don't have a normal distribution? Let's go back to our little thing that we had before, our StatCrunch thing. But this time, I'm going to go ahead and do it again. Okay, so this time we're going to do it, but instead of it being a normal distribution, we're going to go ahead and do a right distribution, a right skew. So it's not normal, okay? The mean is still going to be, it's going to be skewed. It's going to be skewed to one side. So do you see this distribution right here? Is that a normal distribution? Okay, so let's go ahead and take samples. Now, this time we're going to take samples of 3 each time. Now, I'm going to take 1,000 at a time. So I took the first 1,000 samples, take a 2,000 sample, 3,000, 4,000, 5,000, several thousands, thousands and 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 thousands. Okay, so now we have the distribution of this distribution right here. That's the distribution of the sample means. Does that look normal? No, it's skewed because this one is skewed, right? Now look what happens when you change your sample mean, your sample size from 3 to 30. Okay? So I'm going to do the same thing, but I'm going to take it 30 in the sample. There's 30 things in the sample. So I'm going to take it thousands and thousands and thousands and thousands of samples. So we're going to have thousands and thousands, and I keep having to do more and more. I wish they had one that was 10,000 at a time, because you want to take tons and tons of samples at one time. Okay, so what do you see about that distribution of the sample means?
It's becoming normal.
It's becoming normal. Okay? So that's what this theorem is saying. If X has any distribution with a mean of mu and a standard deviation of sigma, then the sample mean based on the random sample of size n will have a distribution that approaches the normal distribution with a mean mu and a standard deviation of sigma divided by the square root of n. That's your standard error. Okay? That's the central limit theorem. As long as your sample size is 30 or more. That's the key thing. You have to have more than 30. So where does that apply to you in your problems? Your problem is going to say, assume it's normal. You don't have to worry about it. But if the problem doesn't say assume it's normal, or it doesn't say anything about normal distribution, you have to look at the sample size and make sure it's over 30. Okay? If you go to another research class, like for example, you're in psychology, and you have a research class, then one of the things they're going to say is when you do your sampling, make sure you have 30 in your sample. So that way you can assume normality. Okay? You can use the central limit theorem in this case. So the central limit theorem says as long as it's 30 or larger, you can have a normal distribution. Now let's look at this one right here. Let's say that we have this one right here. Records indicate that the package shipped by a certain trucking company has a mean weight of 510 pounds and a standard deviation of 90 pounds. 100 packages are being shipped today. What is the probability that their mean weight will be more than 530? Notice how I underline mean, because that's your key thing. That's the key thing when you're looking at these problems to look at. If it says, what's the probability of an individual number, then you're just going to do it what you had before. But if it says, what's the probability of the mean, whatever it is, in this case, a mean weight, then you're going to have to use the standard error. Okay? So in this case, we have 100 packages. Is that greater than 30? So we can assume normality. Okay? So now, what we're going to do is we write our numbers. Our mean is 510, our standard deviation is 20, and our sample size is 90. Then what we're going to do next is we're going to convert it into z-score. X bar, in this case is X bar is greater than 530. So now I'm going to take X 530.
Wait, I thought the standard deviation was 20. I mean 90. Yeah.
Okay, so I'm going to go from here then. Okay, so we have this. So we're going to go over here. That's an error, that's a typo somewhere. So we have, our mean was 510. Our standard deviation was, what did we say? 90. Okay, and our sample size was 100. Okay, so our next step is going to be to find our z-score. So our z-score, now we have to find the standard error. So our standard error is going to be 90 divided by the square root of 100, which is what? 9? 90 divided by 10? Okay, so that's our standard error. So now we have to find our X bar. So that's more than 530. Our probability is that X bar is greater than 530. So now we have 530 minus the mean of 510 divided by 9. Okay? That's my standard error. So we have 530 minus 510 divided by 9. And we get 2.2 repeating. So our z-score is 2.2 repeated. So now my probability is going to change to z-score is greater than 2.2 repeating. And now we're going to go ahead and do that. We're going to go ahead and do second vars, normal CDF, 2.22, comma, 1 e to the 99. And press enter. And you get your answer, 0.0132. Okay, so that's going to be your answer. So we're right there. Okay, so any questions on that one? Okay, so we're out of time, so we'll continue here at this point, okay? So keep on working on the worksheets.